Okay, so thank you again to the organizers. I'm having a really good time here. Not only is it nice to hear talks where I understand everything, because the talks are so good, and B, they're sufficiently close to my area, but also I'm learning a lot of new things, and the way the organizers have grouped the talks together, I'm finding that really, really beneficial. So as a case in point, for today, we're going to be generalizing all the things that I did on Monday. We're going to be generalizing those to the case of higher rank, and then to SL3. And there's sort of two, well, maybe this is a very oversimplification, but there seem to be two schools of thought about generalizing Fuchsian groups. One, you can, which is the way that I kind of grew up, you can generalize them through Kleinian groups, and so you go to quasi-Fuchsian groups in the world there. But there's a new and a more fashionable way that you can go sort of to Anosov representations and all of the things that we heard from Tengren. And this is something that I find very fascinating, and I can see lots of beautiful geometry, which is sort of close to the things of my heart, but it's something that I don't know enough about. And so one of my hopes for this time is that I will learn enough, and I've already talked to some people who have promised to try to teach me something about this philosophy. And we're going to see, and there are two sort of fundamental ideas in those two philosophies that are both going to come in this talk, and they're actually at odds with one another. And I mean, the first time we submitted this paper, I'm sure that we had a referee who was from the higher Teichmüller world, and so I realized that we had not made the two different philosophies clear enough in the paper, so we rewrote it, and never know. But I want to bring out that point because I think it's really nice to bring the sort of the Kleinian group people together with the higher Teichmüller people, because we can all learn from, there's different flavors going on. And yeah, and I'm doing this in higher rank just because this is quite interesting and a new world for me. And I know that there are many people who are much more expert. And so I'm probably going to say all sorts of things that are wrong. And I want to learn as well, because you never get too old to be a student and to learn. So that's what we're going to do today. We're going to generalize this construction I did for Fenchel-Nielsen coordinates for SL2R or PSL2R, and then the reinterpretation for SO21. We're going to look at how we generalize that to SL3C, and in so doing, we want to unify the various other generalizations that already exist in the literature. So here's a plan for today. You can see most of the sections have start with the same two words, which just shows that I'm on topic, I suppose. So we're going to start out by recapping what we did last time, and then I'm going to give you the general construction. That's maybe the first half of the talk, of how we're going to generalize this construction to SL3C. And then I'm going to specialize this general construction, and we're going to specialize it into 4 different ways. The first way we're going to do is we're going to specialize it to SO21 and to check that I actually recover the things that we discovered on Monday. And then we've got 3 other classical generalizations of Fenchel-Nielsen coordinates for quasi-Fuchsian groups, for convex projective structures, and for complex hyperbolic groups. And I'm going to show that how we can specialize in all of those 3 cases. And also what I want to do is to draw some pictures of how I think of the way all of these different groups sit together, and how the Fenchel-Nielsen coordinates because there's a beautiful picture that I somehow have in the back of my mind, and so I'm going to draw some cartoons because I can't possibly draw in that higher dimension. So anyway, so that's where we're going, and that's a summary of the talk. So let's just recap what we did last time. I went through the classical geometrical construction of Fenchel and Nielsen, and that was basically had 3 steps. we had to parameterize pairs of pants, and we did that using the boundary curves. I sort of did a quick hand-wavy argument for how you would do that, and then Ara very beautifully drew all these hexagons at the start of the talk, his talk, so that fills in the gap. So that's another good thing with the organizers, that everybody is reinforcing everybody else, so that's really lovely. And so then we had to glue the pairs of pants together, and that meant that I had to have the boundary curves had to have the same length and the opposite orientation. As remember, I'm just keeping an orientation on my surface so that my inside is always to the left as I wander around the curve. I suppose if you drive on the opposite side of the road, you could always have it on the right, but well, I think the statement, somebody once asked me which side of the road do they drive on in India, and I said it's a purely average statement, they drive on the left, but it is a purely average statement. Right, okay, so where was, sorry. Yeah, and I certainly would never want to drive in India. I'm really in awe of the people who do. Right, okay, where am I? I've completely lost my train of thought. Okay, so yeah, we want to glue pairs of pants together, we want to close handles, and we had the boundary curves had to have the same length and the opposite orientation. And then we had a twist parameter, and if you remember, we could twist as many times as we like in both the positive and the negative direction, and that's because if I did a full twist, I end up with the same geometric structure, but I have a different marking, and because I'm wanting to work in Teichmüller space and not moduli space, then I can twist as many times as I like. But when I want to generalize, it's sometimes difficult when I'm ultimately, well, my feeling is I'm losing all of the geometry for when I'm thinking about SL3C, but maybe if I sort of thought about flags and things like this and vial chambers and whatnot, there's lots of interesting geometry, which is a bit too difficult for me, but I want to learn about how that all works. So maybe I could really do some geometry in that case. So I want, but my sort of naive way of doing things, I like to reinterpret things in terms of matrices. So we did the first way of doing it in terms of SL2R, but then, excuse me, I converted to SO21 because I want to be thinking of 3x3 matrices. And the three steps were, instead of using boundary lengths, we use traces to parameterize the pants group. So again, three traces with a very mild extra condition will determine my representation. Mild condition being a sign of a certain square root. Then we had trace identities for gluing and handle closing. So once again, so if I glue two things together, now the elements corresponding to the boundary curves, they have to be, one has to be conjugate to the inverse of the other. And then we wanted to reinterpret our gluing parameter, and so when I have a boundary curve, then I looked at elements that have the same eigenvectors, matrices with the same eigenvectors, so something in the centralizer of that element, and then I chose an eigenvalue, and that gave me the gluing parameter, the hyperbolic distance, which I have to twist when I twist around the curve. So those are my three steps to happiness. And what we're going to do is we're going to see how those three steps work for the case of SL3C. And then we're going to relate those to the previous constructions, as I've already said. So once again, we are fixing a pants decomposition of my surface. And once again, for the purposes of exposition, when I close handles, I want to always close handles within the same pair of pants. That's not technically necessary for the construction, but it just makes it easier when I'm talking about it. And so my pairs of pants are always going to be Y because they're sort of a Y shape. And then the curves are going to be gamma, and we have our orientations as advertised. Right, so what's the motivation for thinking about discrete groups in PSL2, the PSL3C or SL3C? What's the motivation for thinking of how they act on CP2? This is a motivation that I learned from Pepe Siade, and it starts back with well-known work. Well, there's two strands of well-known work. One starting with Poincaré and Klein, and then working our way through the sort of the complex analysis crowd through alphas and bears and so forth, which is Kleinian groups acting on CP1 and the dynamics of the limit set. We've already had the limit set defined a couple of times, and the domain of discontinuity and things like that. And then the second, well, actually, that was my second one. So the first one is the dynamics of rational functions when you iterate them, and that was Fatou and Julia and so forth. And then Sullivan made this wonderful observation, which is now called the Sullivan Dictionary, that many of the phenomena you see with iteration theory, you also see with Kleinian groups and with the limit sets. And often there's a similarity in the way things are proved, but there's no direct way that you can connect between them. So there's a philosophical way you can match up the different sorts of phenomena you have, and that should give you a guide about how you might go about proving something, a result from one side to the other, but you cannot pass directly, or in very few cases you can pass directly. You have to do separate proofs, but there's a sort of philosophical way of connecting them together. And so then the one side of that diagram, the dynamics of iteration theory, that's been generalized to rational functions acting on CPN. There's various names there, which I shamelessly cribbed from the introduction to their book. But Fornes, Bedford, Smiley, and Siboney, and so forth. And then this question that Alberto Wachowski and Pepe Siade asked, well, what about the other side of the Sullivan Dictionary in higher dimensions? So what can we think about if we want to study discrete subgroups of PSL3C or PSL-NC for higher values of n acting on, well, I should say PSL-n+1 acting on CPN, or PSL-n acting on CPN-1. So what about the dynamics? What can we say? And so this was probably around 20 years ago. They asked this question, and there's a whole slew of really beautiful results that have come out. There's a very nice book by Cano, Navarrete, and Siade called Complex Kleinian Groups. I would recommend that book. It's a very nice book. And it also, but the main thing that they have been focusing on, they've been studying the dynamics of elementary groups. So we've already heard about elementary groups. They're groups which have, well, one way of thinking about it, they have a finite orbit, or they don't contain a free group. So my contribution is I've kept saying, well, let's think about more complicated groups, more interesting groups. So what about surface groups? And so I sort of started to think about that, and so yeah, my motivation for this whole idea of the Fenchel-Nielsen coordinates is to build some sort of coordinates which would help me to study the action of surface groups in this context. And a sample result there that Angel and Pepe and I proved was that if you have a surface group acting in SO21, just like the ones we had in the last time, and you allow that to act on CP2 in the obvious way, then its domain of discontinuity has 3 connected components. 3 is a very unexpected number. Right? I mean, for people in the classical Kleinian groups world, you would have sort of 0, 1, 2, or infinity. And in fact, it was the first example that was found with a domain of discontinuity that in this context with 3 components. I'm happy to talk to people about that, but that's not the subject of today. And so the questions we might want to ask is what happens when we deform such a representation, and sort of some discussions that we've had, which haven't yet quite turned into a project, make us believe that immediately you get infinitely many components in the domain of discontinuity. Okay, so let's start to think about how we might begin on defining our Fenchel-Nielsen coordinates. Now, let's just pause for a moment. What did we have? Well, we had length parameters and we had twist parameters. We had one of those for each of the 3g minus 3 curves that we had in our Pants decomposition. Now we expect to have 2g minus 2 times the dimension of the group number of parameters. The dimension of the group it was 8 complex dimensions, because you think of 3 by 3 matrices, then one determinant condition. And the knowledge bomb that I want to give to you is that 3 does not divide 8. And so if I just wanted to have parameters associated with the boundary curves, then there's something funny going to happen. So I'm going to need some extra parameters. The question is, where do I get them? And so what we're going to do is we're going to just sort of go through the machinery that I was going through on Monday, and let's see where those extra parameters pop out. So before we do that, that's sort of where we're going, but we want to think about these representations. So I'm going to think about surface group representations where every non-trivial element of the group is represented by something called a strongly loxodromic element. So this is a natural generalization of the loxodromic elements in SL2C. Here we have 3 eigenvalues. They're distinct eigenvalues, and moreover, their absolute values are distinct. And without loss of generality, I can order them so that mod lambda 1 is bigger than mod lambda 2 is bigger than mod lambda 3. Okay, so now if you stopped me in the street and handed me an element of SL3C, then how would I determine whether it was strongly loxodromic or not? That's always a useful thing. So here is a nice result from their book. It's based on earlier work by Navarrete. There's a polynomial there, a polynomial in 2 variables, which is essentially where this comes from is it's essentially the resultant of the characteristic polynomial and its derivative. So that would be a thing where you want to check that the characteristic polynomial doesn't have repeated root. And so that's the polynomial. Then a matrix in SL3C is strongly loxodromic if and only if, well, there's 2 conditions, two equivalent things, well, 2 things. First, it may possibly be that the trace of the inverse was the complex conjugate of the trace, in which case you would require that this polynomial then, when I substitute x is trace of A and y is trace of A inverse, that becomes a real polynomial, or it gives you a real value, I should say, and so you would require that should be positive, or in the other case, then that should equal 0. That should not be 0. Let's just pause a moment. When we were thinking of SO21, the trace of the inverse was equal to the trace, but they were both real numbers, and so that's a particular example of this first case. And in fact, if you think of an element of SO21 in here, then that polynomial you can so that would be where you would have both of these things are equal and real, then that polynomial would factor as x minus 3 cubed times x plus 1. That's not something I just did in my head. And so that condition would be that the trace should be strictly bigger than 3, which we know for SO21. So that is, if you take the characteristic polynomial of the matrix and you take its derivative, if those 2 polynomials have a common root, then you would have a repeated eigenvalue. and then you take the resultant, which is a way of calculating. Okay, so yeah.
Is there a way of seeing these conditions, some algebraic conditions, if they are satisfied on SO21, and going back to something that you said?
So for SO21, an element is loxodromic if and only if its trace is strictly bigger than 3.
No, what I'm saying is, are there conditions that say that it's enough to check on SL2C, that is translates, and SO21, that is translates, and that's enough?
Well, for a particular group element, well, we can talk. I'm not quite sure what your yeah. Okay.
Are there cases where the condition, like the condition A is satisfied, the first part of A is satisfied, but in the polynomial, when evaluated, it turns out to be negative, and therefore it's not strongly loxodromic?
Correct, yes. That's exactly going to happen if you have, for example, 3 eigenvalues which are all roots of unity, distinct roots of unity, distinct unit modulus complex numbers, so e to the I theta, e to the I phi, and e to the minus I theta minus I phi. That's exactly going to be negative.
So only when it's negative there's a problem, otherwise not equal to 0, like in part B not equal to 0, and in part A when it's positive, all of these.
Yeah. So the way I kind of like to think about this is, if you think of elements of SL2C, then they're elliptic if and only if the trace is real and lies between -2 and 2. It's parabolic, or the identity, if and only if the trace is real and equals plus or minus 2. It's a tautology. And it's loxodromic if the trace is real and bigger than 2 or less than -2, or complex, purely complex, and has a non-zero imaginary part. And so you could think of this condition as being, if the trace was real, of then being bigger than 2 or less than -2, and this condition as being having non-zero imaginary part. As a sort of it's not quite the same, but it's you can think philosophically of that. Okay. And also, I'm going to want to use the characteristic polynomial a little bit later, and this seems like a good point to do it. So if I have an element of SL3C, this is a general fact, not just for strongly loxodromic maps, that since we have the product of our eigenvalues is 1, that's because the determinant is equal to 1, then the linear term in the characteristic polynomial, well, I can rewrite this lambda1, lambda2 as lambda3 inverse, this lambda2, lambda3 as lambda1 inverse, and this lambda3, lambda1 as lambda2 inverse. But that should just be the trace of the inverse, because if lambda is an eigenvalue of A, then lambda inverse is an eigenvalue of lambda inverse. And therefore, the characteristic polynomial has this sort of almost symmetric form. But one thing to observe is that the trace of A and the trace of A inverse completely determine the conjugacy class, providing I have distinct eigenvalues, distinct roots, which I do in this case. So if I'm a diagonalizable map, then the trace of A and the trace of A inverse determine the conjugacy class, but one of them on its own is not sufficient unless I happen to be in a special subgroup. Good. Right, so now we can roll our sleeves up, and we can actually look at SL3C representations of a free group. This is a result which is it's appeared various points in the literature. The version I'm going to be giving is a mild adaptation of one given by Sean Lawton, but there is a paper of Wen, a compte rendu, which doesn't have a proof in it, but is earlier than Lawton's work. And there's also some version of this in work of Teranishi. And Pierre Ville has also done something else. So I just sort of attached a list of names. It probably goes back to quite a long way. It's probably the sort of thing that some of the 19th century people would know about. I don't know of any earlier references. If other people do, then please let me know. But so the group gamma, the gamma is a free group on 2 generators with as a subgroup of SL3C. That is completely determined up to conjugation by the traces of 9 elements in the group. So you think of, remember from last time, we looked at Fricker and Vogt. This was that would be their result for SL2C, that it was completely determined by the traces of A, B, and C. Well, here, this is the analog of the Fricker-Vogt theorem. But now we have 9 traces. But the dimension of my group is 8. Complex dimension is 8. So that means they must satisfy a relation. And they do satisfy a relation, and that is that there's a quadratic polynomial whose coefficients are themselves polynomials in the first 8 of those traces, and the roots of that polynomial are the trace of the commutator of A and B and the trace of the commutator of B and A. And with that, we're going to have to carry that extra little piece of information along with us. But that's really good, because now I can parameterize my pairs of pants. But when I did my pants decomposition, I really wanted to have things that had this threefold symmetry under cyclically permuting the 3 boundary curves, because I want to just say I've just got some lengths, I've got some other parameters, blah, blah, blah. I don't want to have to say, well, I've got some sort of extra decoration on the pairs of pants so that I know which are my preferred pair of boundary curves. Because that would just extra faff to keep carrying along with me. And so I want to have a parameterization that is invariant when I do a cyclic permutation of the 3 curves, or the 3 generators. And so when we do that, we can see, well, A, B, and C, we can nicely cyclically permute those, and that's okay, that little group. These people nicely cyclically permute amongst each other. The trace of the commutator, we do a little calculation. The commutator of C and A is the same as the commutator of A and B up to conjugation, so they have the same trace. So that's all good, but we've got these pair in the middle. And they don't behave well when I cyclically commute. And this was a problem that when Plattis and I were doing our complex hyperbolic Fenchel-Nielsen course, we came across this problem, and we got out of it using a way which, with hindsight, felt like the right thing to do at the time. With hindsight, isn't so great. We sort of used some cross ratios instead. But then, sometime later, I realized that what we can do is we can symmetrize this trace of A inverse and this. And that's what we're going to do. And we're actually going to prove that. And this is a thing which I'm calling shape invariance. The word shape invariant, well, to my knowledge, it comes from a paper by Ulrich Brehm when he's talking about reflection groups, complex reflection groups. And he wanted, so there, 3 angles don't determine a triangle, but you need an extra parameter, and he called that shape invariant. And this is very much in the same spirit, so I'm liking to call them shape invariants. And that is that if I take this trace of A inverse B, and I subtract off trace of A inverse times trace of B, then that's invariant when I do my cyclic permutation. And similarly, if I take trace of B inverse A and subtract off trace of B inverse trace of A, that's again invariant under doing my cyclic permutation. So let's prove that. It's a really nice proof, and as you can see, it only takes half a slide. Cayley-Hamilton tells me that A satisfies its characteristic polynomial. So here, O is the 0 matrix, and I is the identity matrix. And so we know that A satisfies its characteristic polynomial. So let's multiply on the right by A inverse B, but remember that ABC is the identity, so I can write that as A to the minus 2C inverse, and I get this. So A cubed goes to AC inverse by multiplying by this. This one becomes trace of A times C inverse, and then et cetera, et cetera. And now I take the trace of this identity, and remember that when I have the trace behaves well under addition, and so I can just take this as the sum of the traces, and I rearrange, and then I get the first line on my up there. So this is a really lovely little proof that helps me symmetrize my parameters. And that was the first one, but of course all the others you can guess are similar. So now that gives me the set of parameters that I really want to have for a pair of pants. And what we do is we have 3 boundary curves, and they correspond to strongly loxodromic maps A, B, and C. And I want to have the traces of A, B, and C and their 3 inverses. I've got my 2 extra parameters, complex parameters now are these shape invariants. I have to carry along with me a choice of the root of the quadratic polynomial. And all of this behaves well under cyclic permutation of A, B, and C. And before we leave this slide, there's 2 comments. The first one is this root of a polynomial, the commutator polynomial. In some ways, that's always mystified me, but there's a sort of a way that maybe we can make sense of. So if I were to take my A, B, and C and to swap them with A inverse, B inverse, and C inverse, well now I wanted A, B, C to be identity. I no longer have A inverse, B inverse, C inverse the identity, so we need to swap the B and the C around, the B and the A around. And now the B inverse, A inverse, C inverse is the identity, so that would be another set of parameters, but now the commutator of B inverse A inverse, of course, is just the commutator of BA up to conjugation. That's supposed to mean conjugation. And so now I've swapped the root. So somehow what I'm doing when I'm swapping these roots, it's like making a choice of orientation on my surface. So that's a sort of, to my mind, the philosophical way of thinking about this choice of this root. Yeah? I'm choosing. I'm choosing them. Yeah, I'm saying that a pair of pants is a set of strongly loxodromic elements satisfying that property. I mean, that's the object. I mean, this should be the set of representations that I'm thinking about. Now, we could weaken that slightly. If I were to, I could make them parabolic in some sense, and that would mean that I would have like an infinite end to my, but Fenchel-Nielsen coordinates don't work well when I have cusp surfaces. So that is a generalization we could think about, but it's not one that we want to do today. I could actually weaken it slightly so that they had a repeated eigenvalue. That's gonna mess up my ideas for twisting. So I want to just, for today, we're going to think about this case. There's lots of ways you could think about generalizing this. I know that Krishnendu and perhaps some of his students, perhaps even people here, have been thinking about doing this for higher dimensions and for over quaternions. But the thing that I really want to have, and I haven't yet seen people do in higher dimensions, maybe somebody can correct me about that, is I want something that is cyclic invariant under cyclic permutation, because that way I don't have to put any extra like decoration on my pants decomposition that tells me which order I should put my boundary curves in. And so that's a little challenge for you if you're interested in thinking about this area. I mean, there's a paper I know of Sean Lawton where he gives you parameters for the free group on 2 generators into SL4C and perhaps even SL5C. But I've thought for some time about whether I can symmetrize those nicely, and I haven't been able to do it. But perhaps somebody who's smarter than me can actually find a good way of doing that. And that would be the one obstacle that we would have to then push forward and generalize this to the whole construction to higher dimensions. So that's the one place that I can't do. So I thought I would just really point that out. You're about to ask something, Mahan. Well, it's the choice of a sign. So it's this choice of root of it here, right? And so which you could think of as like an orientation on your surface. But there's a choice between that triple and that triple. Yeah. So it's just a plus or minus sign. Right. Okay. So I think those were the things that I wanted to say on here. So it gives me eight complex parameters, but I have to keep this plus or minus sign floating around. It's a little bit awkward, but I just get one plus or minus sign for each pair of pants. So now, well, I told you about the machine we can run for sort of using group theory to do my gluing and twisting, or at least for the gluing. So we run that machine again. So let's just remind ourselves, because it's a whole 2 days ago, if I want to glue, then what do I need? I need to have, if I glue A, I need to have AA prime, I need A prime to be conjugate to A inverse. Now, I no longer have the trace of A and A inverse the same, but I have to have the trace of A inverse. I no longer have the trace of A and A prime to be the same, sorry. And so I need to have the trace of A inverse as the trace of A prime to be the trace of A inverse, blah, blah, blah. The trace of A prime inverse to be the trace of A. So those are my gluing conditions. They're very simple gluing conditions. And then what I need to do is I take the free product with amalgamation. So I take this group, I take that group, I free product them together, but then I quotient out by the relation of A prime is A inverse. And I end up with that group, which, as I pointed out on Monday, is the representation of the fundamental group of a four-hole sphere. So at some point I was thinking about doing things with four-hole spheres, and I said, well, if three-hole spheres were pairs of pants, then four-hole spheres should be t-shirts. But the word t-shirts for four-hole spheres hasn't actually caught on. But I advertise that just in case somebody wants to do that. Okay, so now we use group theory for closing up a handle. Again, because just for simplicity, I'm just closing a handle within the same pair of pants. Yes, that's not necessary for the construction. So we need to close the handle. We need to have B to be conjugate to A inverse, and so I have those traces there. The trace of B is trace of A inverse. The trace of B inverse is trace of A, and I get an HNN extension. So I have this extra element D that conjugates B to A inverse, and then I get that. And again, the moral is that closing a handle is the same as replacing two generators for the previous group with a commutator. Now let's think about twisting. Now we need to think slightly more carefully about the twisting, because there's new phenomena that are going to come in here. But they're really the same old phenomena, but we just need to reinterpret them in the higher dimensions. So if I change the gluing along A with the matrix K was supposed to represent the twist, then as we had there, and for those of you who can't remember, K, if A was diagonal, then, well, okay, we'll talk about K. Sorry, K is going to commute with A. So K is the thing that I'm going to use for twist. So in the old case, the SO21 case, then if A had been diagonal with eigenvalues lambda 1 and lambda inverse, then K should be diagonal as well, and the e to the T alpha would be the parameter, would be the eigenvalue of K corresponding to the twisting. So I just read off the twisting from eigenvalues. We're going to make this precise on the next slide. This is just to remind you. And then similarly, closing the handle, I put this element K that commutes with A. So it all boils down to looking at the centralizer of A. So that means everybody in SL3C who commutes with A. Because A is diagonalizable, let's just do it in the diagonal case, because we can always conjugate to that case. Right? Okay, yeah, what you would do is, let's take my first pair of pants over here. however many of those I need. Yeah. And now and this is now the axis of A. So it's alpha hat, which is the axis of A. Right. And now I want to glue on this side. So this would be, so this is y tilde, this is y prime tilde. And now this is also going to be the axis of A prime. So A is supposed to go that way and A prime is supposed to go that way. And now if I just take the fundamental group of this object, that is the free product of those two groups with amalgamation. So so I think I said last time, but I always have this sort of geometrical movie going on in my head, which I then sort of put linear algebra subtitles onto that movie, and I'm just giving you the subtitles, and so we need to think of keeping the movie going on in our head. Is that? Yeah, exactly. That's sort of what's going on in my head, is a Klein combination theorem. Yeah, exactly. I guess as soon as I get amalgamation, I have to put Maskit's name, but for just the straight free products, I think I would keep with Klein. But I certainly would call it a combination theorem and not a ping pong. Not necessarily. We'll yeah. I'm not claiming that here. Okay, so let's come back. What I'm interested in is I'm interested in finding a patch in the representation variety that is going to contain all of the discrete and faithful ones that are of the type that I want. That patch is going to be strictly larger than the set of discrete and faithful ones. Now that's, if you're coming from the higher Teichmüller world, that seems rather strange because there it's a connected component. But if you're coming from this is the point I was trying to make at the beginning, if you're coming from the quasi-Fuchsian world, it's completely natural because you know that quasi-Fuchsian space should have some sort of fractal boundary, and there's no way that I can give you exact coordinates that would describe that fractal boundary just in terms of linear things. So yeah, I'm just creating this big patch. So yeah, maybe let's draw this. It's a good time to do it. So if here is my big representation space, and then here are my discrete and faithful ones, then I'm putting coordinates on a patch like that contains all of the ones I want. And maybe it goes up. Maybe this relates to your question. Maybe it goes up to the edge, and maybe so maybe there's some. Maybe I should actually draw it as if it sort of has places where I could sort of get very close to the edge or something like that.
So how do we know that the differentiated prime actually has this presentation?
That's just combinatorial group theory. Right. So what do we? So so. Okay. Sorry. I'm just doing this at a group theory level, but yeah, then well, you could there could potentially be some new elements and then I would have landed in this sort of space here if I've suddenly got an accidental parabolic or an accidental elliptic here. I'm just constructing a representation of it. I'm not really claiming that it. Yeah. I'm certainly not claiming it's faithful. Certainly not claiming it's faithful. Because if I land up here, I will be able to find points where it's not faithful. Right, okay. Right, so now we wanted to look at the centralizer of A. A had distinct eigenvalues, so I can diagonalize it. And so let's diagonalize it in the obvious way. And now I'm going to follow Goldman here. He decomposes K, he has a different letter for it, but into two things called S and T. It takes the product there. And the first one, it should have a 1 in the middle space, and then the other two are complex conjugates of each other, or inversions of each other. And the second one, the top and the bottom one should be the same, and then the one in the middle should be the should make it have determinant 1, so it should be the square of the reciprocal of the other one. And I'm going to give names to all of these things. So I'm going to give names of T, theta, S, and phi. T is going to be called the twist. Theta is going to be called the bend. S is going to be called the bulge, and phi is going to be the turn. So twist is, this is a spoiler alert. The twist is going to be the original Fenchel-Nielsen twist here. Theta is going to be the bend from the twist bend construction from Kleinian groups. The bulge is going to be Goldman's bulge parameter from the convex projective structures. Phi is a sort of a thing that's going to come in from the complex hyperbolic case, which we called turn. So we called bend at the time, but it was clearly different. So we've introduced this new name called turn. So, but twist, bend, and bulge, turn, they're complex parameters, and those are going to be the things that we're going to have as a generalization of our original Fenchel-Nielsen twist. Okay. So let's recap all of that. So I'm going to have a bunch of free groups on two generators, which are going to be the fundamental groups of my pairs of pants. And I'm going to have representations of those into SL3C. So I can just think of two generators, three generated with ABC equals identity subgroups of SL3C. So they're completely determined by the data of the three boundary traces, the three boundary inverse traces, the two shape invariants, and some choice of orientation, which is coming from this root of a quadratic polynomial. And that gives me 16g minus 16 complex parameters plus 2g minus 2 choices of sign. I then use the Pants decomposition as a recipe to glue. And then when I do that, I need to have that the trace of AK is the trace of AJ inverse, and the trace of AK inverse is the trace of AJ for gluing, and the similar thing for the handle closing. So that gives me, so I go down from 16g minus 16 complex coordinates. I now have 6g minus 6 complex conditions, and so I'm left with 10g minus 10 parameters. But now when I glue or twist or close, then I have my two new complex parameters, the twist bend and the bulge turn. And there's one twist bend and one bulge turn for each of the boundary, each of the Pants curves, so there's 6g minus 6 of those. And so I put those in, and I get 16g minus 16 complex parameters plus 2g minus 2 choices of sign. And those are my Fenchel-Nielsen coordinates for SL3C. We've achieved our first goal. Let's see if I'm going. Yeah, that's probably about right. Slightly more than half the lecture. Yeah. Sorry. Yep. So what these. Right, we're not going to have the phenomenon that you have for for real Fenchel-Nielsen coordinates that any set of parameters are going to give you a nice thing. But we didn't have that for SL2C either, for the quasi-Fuchsian groups. That's one of the things you lose when you generalize. I mean, you're a higher Teichmüller guy, and so, or a higher rank guy, and so for you it's natural that we should parameterize a whole component. Whereas as a quasi-Fuchsian person, I'm saying no, that's not natural at all. And so somehow we've sort of got to have a trade-off of these. But what I can say is, well, to say that those were all loxodromic, then I gave you a condition for what those numbers would have to satisfy to give me loxodromic maps, strongly loxodromic maps. That's all I need. Right? That Cano Navarrete Siade condition. That would give me what being strongly loxodromic is. Here, well, I mean, secretly, I'm going to want these guys to also be strongly loxodromic because I'm thinking of only having strongly loxodromic representations. So you could probably cook up some conditions there, slightly more difficult, but it's not too difficult. And then here, I mean, in principle, you could have any parameters here, but certainly we know that in the quasi-Fuchsian case, there are certain parameters you can't have. And so yeah, it's not quite as nice as you might hope. Is that answered? Yeah. Right. So now let's just check that what we've done now. If I just restrict back to SO21, let's just check what happens, and I haven't done anything funny and gone awry somewhere. Okay, so when we had strongly loxodromic maps, well, if I just think of a strongly loxodromic map that is also in SO21, that is just a loxodromic map. And it's determined by one real parameter, namely the trace. And so when I used to have two complex parameters, then now I have one real parameter. So I'm going to. So let's just imagine that this is the space of all my SL3C. Right, so let's just imagine that that's my SL3C parameter space. That's a 16G minus 16 dimensional space. I can't possibly draw that. So that's my cartoon of it. And here in the middle, that's going to be my, so hopefully the colors show up a little bit. I noticed they didn't show up too well when I was in the audience, and that's my SO21 space. I'm sort of thinking of that as sort of sitting inside my big space over there. I'm drawing it as a point. Of course, it's a Teichmüller space. It's got 6G minus 6 real coordinate dimensions, but at the moment, because it's a cartoon, I can draw it as a point. So now that point, in terms of my coordinates, I can say, well, okay, I had some parameters, then the fact that those two are equal, that's like on a diagonal slice, and also the fact that they're real, that also cuts out some, so that's a linear condition on on my parameters. And similarly for the others. So this is cutting down to some linear conditions here. Now, from the previous lecture, we talked about what the trace of A inverse B was in SO21, and it generalized this Fricker equation, and you needed to have a choice of square root coming in, but with Gilman and Musket, we showed that was a positive sign because the square root we would have to have a negative sign, and so two negatives make a positive. So that is completely given that this shape invariant, that both shape invariants are equal, they're both real, and they satisfy that equation. So unfortunately, that's not a linear condition. It's some sort of subvariety sitting inside my big space, but that's the only thing that's slightly wrong. But maybe I could have tweaked my shape invariant coordinates so that was linear as well. Quadratic polynomial with those two things are the same, so that has repeated roots, so I no longer have a choice of sign there. So now the pair of pants is now completely determined by the three traces and the sign of this square root, but that was just whichever traces we chose as before. Okay, so now the twist parameters, if I come in here, then we want this twist map K to live in SO21. That's the only restriction I make. Well, we know that, that an element of SO21 should have an eigenvalue of 1. And so you can see that here we must get the identity map. It has to be real, so the thetas disappear. So theta and S and phi are all 0, or else we end up outside SO21. So that's the twist parameter that we had before, because remember we had e to the t1, e to the minus t. Excuse me. So my Fenchel-Nielsen coordinates are the three traces, the relations, and the twists coming from the K. So that's exactly the same. So really, what I've done is a proper generalization of the Fenchel-Nielsen parameters we had before. Yeah? Just hold your horses, that's coming up next. Right, so now we're going to talk about quasi-Fuchsian groups, right? It really was the next slide, yeah? So here, this is my little picture just to remind people what quasi-Fuchsian groups are. They look dynamically on the sphere like a Fuchsian group, except the limit set, instead of being a round circle, is a fractal curve. And this is a sort of little picture here. So that's just to give you a flavor of what we're talking about. And so last time, so we're going to, well, quasi-Fuchsian groups, we're going to consider discrete, faithful, totally loxodromic representations, and I want them to be continuously deformable back to the Fuchsian groups. I don't want to have any of these sort of exotic things that I have by grafting or whatever. And so for those groups, Kouriotis and Tan, they independently generalize Fenchel-Nielsen coordinates, and they're basically complex versions, which is exactly what Mohan was saying a moment ago. They're complex versions of the classical ones. So instead of having, so your length, instead of just being a length along a geodesic, is a length and a twist around. So you think of it as like a corkscrew going round. And so now we're going to compose such a representation with the irreducible representation. It's the same, algebraically, it's the same as the one we considered in the last lecture, except that now it's got complex entries. So remember last time we showed that when we landed in SL3C, or SL3R, actually SL3C, before the SL2R or PSL2R landed in the 0 of a quadratic form. It still lands in the 0 of that quadratic form. So we still are ending up in the orthogonal group of that form. But because we're now working over the complex numbers, the signature of the form does not make sense, because I can conjugate by something which changes the sign of any eigenvalue. And so that's going to be in SO3C. So that's my notation for the orthogonal matrices with respect to that particular quadratic form, but with complex entries. Okay, so now quasi-Fuchsian Fenchel-Nielsen coordinates. We have our three traces. A trace of the inverse is equal to the trace as it was before. We're going to have shape invariants, which are going to be given by the same equation. Now for the choice of the sign, I have to be slightly more careful about the square root, but because I can deform continuously through to a Fuchsian representation, and I never go through a place where the thing inside the square root is 0, then I have a well-defined branch of the square root on which I can analytically continue to make sure that formula is well-defined. Again, the commutator polynomial has got repeated roots, so I don't have any choices there. And then this is exactly as you just said, so let's just come back a moment to this. So here, to be in SO3C, I still need to look like that. And so I end up having a twist and a bend. And so that's exactly the twist and the bend that Tan and Kouriotis found. So that's exactly what you were saying a moment ago. In SO3C or in PSL2C, no. Right? So if we come back to where we were, right? So in SO3C, then S and phi are both 0, but I do get a twist bend parameter. The reason is I need to still be in SO3C, and there I still have to have this eigenvalue of 1. Right, so now let's look for SL3R. So these are convex real projective representations, and here's a image that I've stolen from Goldman's paper. Now when you're thinking of these groups acting on RP2, then you have the domain of discontinuity. It used to be a round disk when it was in SO21. Now it's a convex set. And you get these beautiful tessellations of these convex sets, which I remember when I first saw them, I was just absolutely blown away. I think they're rather beautiful things. Okay, so now we're going to think about representations to SL3R, discrete, faithful, totally loxodromic, continuously deformed through such representations to Fuchsian representations. Oh, before I move on, so let's find a different color. Let's choose a yellow. This is going to be that is my SO3C. Some sort of, it's not quite a linear slice because of this this subvariety for the shape invariance, but it's almost a linear slice. Okay, so now, right, so then, where am I? We're continuously deformable to the Fuchsian representations, and the domain of discontinuity is a convex set. Goldman had these beautiful Fenchel-Nielsen coordinates. So he had parameters with lambda A and tau A there to do with eigenvalues and traces. It's not quite what I had, but it's easy to pass between those to the traces. There was internal parameters. I'm not sure whether did Goldman actually use the word internal parameters in his paper. I don't think he did, but anyway, I think somebody used the internal parameters. Maybe it's you who used internal parameters. They're called S and T. I already have an S and T, so I'm just going to put a Y on them to check that we're not getting confused. So the SY, it's a symmetric parameter of the cyclic permutation. The T is not, but the one little piece of Tengren's work that I'm using, he symmetrized that parameter, and so which is now called R. So you get these two internal parameters, S and R. So now, if we do our Fenchel-Nielsen coordinates, strongly loxodromic becomes loxodromic. So the trace of A and its inverse are now distinct, but they're real. So that's again some sort of linear condition. The shape invariance, well, this is a bit that we're finding a little tricky, but we can certainly write our parameters in terms of Goldman-Zhang parameters. Yeah, and we can show that it's locally bijective, but we haven't actually got a good formula for the inverse of that. And then there's a sign parameter coming from the traces of the commutator, and then with this here, the Goldman. Well, we need to have theta and phi both real for it to be a real matrix, and Goldman showed that he had this twist parameter as well, but then there was this bulge parameter. And the way I like to think about the bulge parameter is if I were to take, it's easier to draw with ideal triangles, so if I were to take an ideal triangle inside the disk, if I was in SO21, again, I'm drawing this is really bad, I'm drawing a Poincaré picture when I should be drawing a Klein picture, but sorry. Now there's a sort of cross ratio condition that would say that those have to lie in a circle, but if I was deforming in this case, then it would lie outside, and And that would be, and then you should think of this convex set bulging out in that direction. Very rough cartoon. So that's why you call it a bulge parameter. At least that's my understanding of it. And so that was, Goldman used that. And so that's exactly corresponds to his parameters. Okay, so 4 minutes left, that's great. So now if we want to think about the SU, so before we do that, let's draw another slice on here. What color haven't we used? We haven't used red. So somehow we're coming through in this direction as a linear slice. So this would be the SL3R. Now I'm going to think about the SU21 case. So the quadratic form, the same quadratic form we had previously has now become a Hermitian form. And so we do have good signs for the eigenvalues, and so it still has signature 2,1. We're going to consider representations to SU21, which are discrete, faithful, totally loxodromic. So here, there are multiple components depending on the Euler characteristic, and they're parameterized by the Toledo invariant. So that we have Toledo invariant is equal to 0 here, and here it equals minus the Euler characteristic, and here it equals the Euler characteristic, and then there's an even number. So yeah, whatever the correct number is, I can never remember. It's like 2g minus 2 minus 1 or something. These components, and the SO21 representations live in here. The end components, these correspond to reducible representations corresponding to Fuchsian representations, direct product abelian representations. And so they might be interested, and that we can completely describe those. So we're going to be thinking about things that live in the central component, the Toledo invariant equals 0 component. For simplicity, we could probably put Fenchel-Nielsen coordinates on the other ones, but for today, let's just think about the ones in the same connected component as the Fuchsian representations. So we gave Fenchel-Nielsen coordinates of Plattis and I. It was given by some. We only focused on 2 of the boundary curves. This was our mistake. We're given by the traces and the cross ratios of the fixed points of those. It was not symmetric, and we had to then do a horrible change of variable formula when we changed which pair of boundary components we wanted to. So those 3 cross ratios, it looks like they're 3 complex numbers, but they again they live on a 4 real dimensional variety, and the ambiguity in the third one is the same as the choice of the roots of the commutator. Okay, so now let's sort all that lot out, and we'll do Fenchel-Nielsen coordinates again. Strongly loxodromic becomes loxodromic. The trace now satisfies the trace of the inverse is now the complex conjugate of the trace. So again, that's a linear condition, but it's a different linear condition from the previous 2, but restricts to the Fuchsian one in the Fuchsian case. The shape invariants, again, they're variables we need to consider, but the one for the inverse is the complex conjugate of the other one, and there is a sign parameter coming in here. And when I do this TS business to look for the twist and the bend and the bulge and the turn, we discover that the twist is 0 and the bulge is 0, but we do get the bend and the bulge are 0, but we do have a twist and turn. So this is not a complex parameter, but it's a pair of real parameters. And so we can draw this, maybe in blue, I think is a color I haven't used. It's sort of coming as a sort of a linear space up there. All of these spaces intersect only in the Fuchsian representations, but they all do contain the Fuchsian representation. So they sort of give us directions that we could perhaps travel on if we were explorers trying to explore this space, and we could all go in different directions. but it would be really quite nice to understand what's going on. We know that if we're coming in the SL3R direction, which I've drawn in red, then I'm going to get a whole component of the SL3R space sort of sitting inside this bigger SL3C space. But certainly in the Fuchsian and in the complex hyperbolic ones, we can deform to the boundary, and so we can go beyond the place where I'm discrete and faithful. So I'll probably either be non-discrete or non-faithful, and so we really do have a patch in the space like that. Okay, so those were our Fenchel-Nielsen parameters, and again, I can convert back to the cross ratios and so forth with our other ones. So that's a summary. So for the irreducible representation of SL2R, we get 6G minus 6 real dimensional subspace, which is the central dot that I have over here. So this central dot here is this 6G minus 6 dimensional subspace. For the SO3C, then I'm going to have, which one? They were the yellow ones. They contain that dot, but it's now a 12G minus 12 real dimensional subspace. The SL3R, which were the red ones, they're now a 16G minus 16 dimensional real space. And the complex hyperbolic ones, they're another 16G minus 16 dimensional space coming through here. But everybody intersects in the middle, and it sort of gives me nice interpretations of all the rest of the coordinates. So the bell just went, and so I'm going to say that's it. Thank you.
Any questions?
What can you say about SLNC?
Well, for SLNC, I would need to be able to get a good parameterization of the free groups on two generators, perhaps in terms of traces or other natural invariants. And I want one of those which has got this threefold symmetry. And so if I can do that, that's the sort of the difficult bit that I don't know how to do. Then we can run the rest of the machinery, and what I would need, I would have various conditions that would say that I could glue, which would be saying that A prime was in the conjugacy class of A inverse, which would be, I would have to now make sure I identify all the elements in the characteristic polynomial, or the coefficients of the characteristic polynomial in the appropriate way. And then what else would I need to do? I would need to do my twist, bend, bulge, turn. And I would need to analyze the centralizer of my strongly loxodromic maps there, or whatever the equivalent of those strongly loxodromic maps I decided to use. And then I would need to be able to parameterize that centralizer, and then perhaps, hopefully, give some geometrical interpretation. So I think this is entirely doable. I think it's also should be doable if we work over maybe the quaternions. Now we don't have traces, but we should be able to characterize, give some sort of characterization of quaternionic representations. Again, I don't know how much has been done in that. I know Krishnendu is interested in that. So there are lots of. So for example, we could take my quaternionic representation and smash it into a complex representation of twice the size, and then perhaps we can use traces there. So there's lots of things we could do for generalizations, so what I wanted, I think I said at the very beginning, I wanted to advertise that this is a sort of a machinery for studying representations of surface groups. I've sort of set out what the machine is like, but it's up to you to put in your favorite group at the beginning and see how we need to adapt the machine in order to be able to cope with that. And I'm particularly interested in these surface groups because of their action on CP2, but I know that we have the higher Teichmüller people who are probably interested in flag varieties and complex flag varieties, and I would also be really interested to learn about that so I can tie those two things together. So I want to come and learn about all of those things. So I'm really happy if people would be able to explain those.
Well, what about punctured surfaces, like with, let's say, some unipotent boundary?
Right.
boundary?
Okay, so now, yeah, so for punctured surfaces, we then, I'm not actually aware of whether you can do some sort of Fenchel-Nielsen coordinates for punctured surfaces in the classical case. I think just depend. I suppose you can, in some sense, because you know something about the parabolic maps there. But yeah, there must be some sort of difficulty. But then you would have to now work out how to parameterize the parabolic ends and so forth. But in principle, it should be doable. Work out how to convert your geometric data into representation data, and how to interpret the gluing and the twisting in that representation world. I don't see any difficulty. It might be difficult to get exact parameterizations because things to do with. So for example, if you take the Toledo invariant here, if I now take a punctured surface instead, that now becomes a real interval. The Toledo invariant can take any real value in this interval between the Euler characteristic and minus the Euler characteristic. But the holonomy around the puncture or the punctures, that is what gives you that effect. So there's somehow all the different things that made it an integer value, you push those up the cusp and you get some twisting going on.
Choice of signs. Maybe one way to look at it somewhat more symmetrically is there's a choice of permutation of A, B, C that you start off with.
Yes.
And if you add that on, then it's probably a choice of a Weyl chamber that you're really doing, which is
Yeah. There's probably some better way of interpreting that. And yeah, if you've got That it was very mysterious to me for a long time until I sort of suddenly started to think about this pair of pants picture and then swapping things over and changing. Yeah. Can I say anything about discreteness? So you should be able to use some sort of, I mean, this is effectively something like a Schottky group. And so, I mean, Ohshika and Siade, they looked at Schottky groups in SL3C. I think they have a slightly different definition of a Schottky group, so we might have to adapt that. But you should be able to give some conditions. I mean, it's not going to be very clean because there's all sorts of curves on the pair of pants that we could shrink, and so you know. But in principle, you should be able to find a big chunk of parameters where you know that it's discrete and faithful. Then, okay, so here's a thing. So if we were to think of just representations of the free group to SU21, so think of a pair of pants group in SU21. Now let's pinch the boundary curves so that it becomes like a three-punctured sphere. In the classical Kleinian world, there's nothing else you can do. You can't pinch anybody else. Actually, here we can. Let me get this right. I think there's another 4 curves that I can pinch on there in the SU21 world. So you end up having a representation of the free group on 2 generators where 7 curves have become parabolic, 7 conjugacy classes. There's actually a 1-parameter family of those. I have no idea whether they're discrete or not, but that's the sort of problem that you can have. So that was a result of Pierre Will and mine. So there's a whole zoo of interesting things, and yeah, that's a good question, but I don't know the answer.
Okay, so if there are no other questions, then let's thank John again. Let's break.